In this video, we're going to talk about another continuous distribution, the gamma distribution, and then a special case of that distribution, which is the chi-squared distribution. So, much like we did for the exponential random variable, we're going to do a Poisson random variable again, have the parameter be lambda. W is going to be the waiting time again, just like it was for the exponential distribution, but in this case it's going to be the waiting time until the what we'll call the alpha occurrence of x rather than just the first occurrence. So first we'll think of alpha as a positive integer, so maybe it's the 5th occurrence or the 10th occurrence, what have you. So we're first going to find the CDF of w just like we did for the exponential. So we're going to do it in the exact same fashion. Capital F of w, that's the probability that w is less than little w. Write it as a complement. Now again, x is a Poisson random variable. We're going to see how many occurrences there are, but we want the alpha one to be past time w. That means there has to be fewer than alpha in the first w time, that first w time interval width. All right, so again, x is Poisson. Lambda is for unit time interval, so the mean for the Poisson here will be lambda times w, scaling it again. Instead of like the exponential when we had no occurrences, this is fewer than alpha, so we'll have to do this as a sum now. So we'll add up from I equals 1 to alpha, or excuse me, I equals 0 to alpha minus 1, so I is representing the number of occurrences, and then this is just the Poisson PDF with parameter lambda w. Okay. All right, so we're going to find the PDF now. We'll take the derivative. The derivative is a little bit messy, but we'll get through it. So let me go back to the previous slide. Here is your CDF. The 1 will go away when we take the derivative. The first term is a 0, which makes this lambda w go away. So it's just as an e to the negative lambda w. So we'll differentiate that separately. Then everything else, when I goes from 1 to alpha minus 1, we're going to have to do a product rule. Okay, so here is the derivative when I was equal to 0. We didn't have a lambda w term. Here is the derivative using the product rule for the top. So we had lambda w to the I, e to the minus lambda w. So here we're using chain rule to take the derivative. Here we're also using chain rule to take the derivative. And now the rest of it's just algebra to try to simplify some things and make it look pretty. Okay. First thing, let's factor out a negative lambda e to the minus, or excuse me, a positive lambda e to the minus lambda we're going to factor out here. Nope, I was right the first time. It's a negative because we'll take negative the negative and make it positive. So we're factoring out a negative e to the negative lambda. So it's going to flip this sign. All right, so this will be gone here. This will be gone here. We're going to split it at the plus sign, and then we're going to cancel an I with an I factorial. So left in the right term, if you will be lambda w to the I over I factorial. Left in the I minus, the left term is I minus 1s instead of i's. Okay, just writing out the sum and just start plugging in things for I, we notice that we get some cancellation, right? This term matches with this term will match with one that's over here, and so on down the line. We're going to get things that cancel. We're going to get this telescoping sum idea again. The only thing that's going to survive are the minus 1 here and this lambda w to the alpha minus 1 over alpha factorial. Except that that's not an alpha factorial. That should be an alpha minus 1 factorial because we only went to alpha minus 1, and this should be an alpha minus 2. So I apologize for the typo there. So this one should be alpha minus 1 factorial. This should be a 2 here. All right, so then when we simplify, this is what we get. Oh, and also notice one more thing. This minus 1 here gets multiplied by this lambda e to the minus lambda w, and it'll cancel with this one out in front. So the only term that survives is this one right here, and it gets multiplied by the lambda e to the minus lambda w. So there's what we get for the PDF. Now again, just like what we did for the exponential distribution, we're going to let theta equal to 1 over lambda. This makes your PDF equal to this. My goodness, I keep making typos. This should be a w, not an x. So the way I have it written with w here. So it's w to the alpha minus 1, e to the minus w over theta, alpha minus 1 factorial, theta to the alpha. When we developed this, of course, I just mentioned at the beginning that we assumed that alpha was an integer. Of course, this may not be the case. It could be that alpha is a half. It could be alpha is 5/3. It doesn't really matter what alpha is. Okay? As long as it's something bigger than 1, we should be able to deal with this. So we need to have a generalized factorial function. So to that end, let's consider this integral. And let's see why this looks like a generalized factorial function. So if we use integration by parts, let's let u equal the x to the power and dv be the e to the minus x. Then we have u times v, and this should be negative here. There should be a negative out in front of this one, because the v part should be a negative e to the minus x. So it should be minus x to the alpha minus 1 e to the minus x. This is v du. When we take the derivative, we should get an alpha minus 1 times x to the alpha minus 2, and then the negative makes this a plus. That's why this is a plus out in front. Integral from 0 to infinity of that, the v du part. Now, even though I forgot the minus sign here for a typo, it's not going to matter. As x goes to infinity, this is going to go to 0 faster than this goes off to infinity. So this becomes 0, and then of course when we plug in 0 for x, we get 0. So this piece just completely goes away, the first piece. So here we're left with alpha minus 1, and notice that this form has the same form as the original integral, except that my exponent on the x has been decreased by 1. So this is gamma of alpha minus 1. So gamma of alpha is equal to alpha minus 1 times gamma of alpha minus 1. So when alpha is 1, we see that gamma of 1 will be 1. It's not too hard to see that, because if we put a 1 in for alpha, we get x to the 0, and then that improper integral will just be 1. So this formula tells me that when I put n in for alpha, I get n minus 1 times gamma of n minus 1. Then I would get n minus 2 gamma of n minus 2 all the way down until I get to 1. And so I get n minus 1 factorial. So that's why this particular integral is a generalization of the factorial function. So this is what we call we use gamma of alpha to describe the alpha minus 1 factorial. All right, so this gives us our PDF of our gamma distribution with parameters alpha and theta. X to the alpha minus 1 here, e to the minus x over theta here, gamma of alpha, theta to the alpha. So this is our gamma distribution. All right. Well, let's find the moment generating function first and then find the mean and the variance, because it's a little bit easier to find the moment generating function. As usual, we'll find the expected value of e to the tx. So we take e to the tx and multiply by the PDF. Now let's play around with some things. Let's move the gamma of alpha out front and the theta to the alpha out front. And then add our exponents here, and I'm going to factor out a negative x after I do. So I get a negative x times 1 minus theta t all over theta. And now let's do a substitution. Let's let u equal that exponent, and then du will be 1 minus theta t over theta dx. Notice that as x goes to 0, or excuse me, when x equals 0, u is also 0, and as x goes to infinity, u goes off to infinity, as long as t is less than 1 over theta, just like it was for the exponential distribution, by the way. As long as I restrict my t to be less than 1 over theta, this will go off to infinity. All right, so now we need to adjust by this constant, the 1 minus theta t over theta, so that's why we've got the reciprocal out in front now. Solving for x, we do theta over 1 minus theta t times u. That's to the alpha minus 1, e to the negative u du. So now I'm going to pull this rest of this constant out in front, and then do 0 to infinity of, this should be an e, not a d. I don't know why that has a d in there. That's a really bad typo. This integral is u to the alpha minus 1 e to the negative u du. Notice the form of this is the gamma function. This is gamma of alpha. Okay? Over here, your theta to the alpha minus 1s cancel each other out. Okay? Up here, notice this became theta to the alpha minus 1 because this theta canceled with one of those. So these two cancel each other out. The gamma of alphas is going to cancel each other out. When we combine these two together, then we get this nice, simple moment generating function, 1 over 1 minus theta t to the alpha. By the way, notice this looks a lot like your exponential distribution moment generating function, right? It was just 1 over 1 minus theta t. This is 1 minus theta t to the alpha. We can think of gamma distributions as a bunch of exponentials stacked on top of each other alpha times. So that's what's going on with a moment generating function here, just as a precursor to things that we're going to do later. So now that allows us to find the mean and the variance rather fast. Take the derivative, we get this for our derivative, plug in and take our second derivative, we get this for our derivative. I'll let you check those details. Those really are the derivatives. Plug in 0 for t, I get 1 on bottom, so I just get alpha theta. Plug in 0 for t into the m double prime, I get alpha times alpha plus 1 theta squared, and then a minus alpha theta quantity squared, and that simplifies to alpha theta squared. So notice this looks a lot like the mean and the variance for your exponential distribution. You just multiply the theta and the theta squared by the number of occurrences that you're looking for. Kind of makes sense. When you think about exponential as waiting time until the first occurrence, this is waiting time until the alphth occurrence. So if you want the mean waiting time, you'll take that many thetas together, waiting time, to get your mean. A special case of the gamma distribution pops up for what we call the chi-squared distribution. This happens when alpha is r over 2 and theta is equal to 2. By the way, this has a lot of applications. You'll see this a lot of times in second semester when you take this mathematical statistics class. This has a lot to do with the distribution of the variance of the distribution and the variances of a distribution. When we just plug in r over 2 for alpha and 2 for theta, this becomes the PDF for the chi-squared distribution. And it's not hard then to use the formulas above to see what the mean has to be, r. The variance is 2r, and this is your moment generating function. The r is called the number of degrees of freedom for the distribution, and that has to do when you start doing stuff with sampling later on that talks about how many things are actually in your sample. So that is material that you'll talk about next semester, but I wanted to give you a little precursor into it because we'll touch on the chi-squared distribution later on this semester. But for right now, we'll just talk about this is what the distribution is. So we'll talk more about these and do some examples in class on Wednesday.